Swayam Prabha. Digital India. Educated India.
Namaskar. So, yesterday in the class we discussed about the resistance, inductance and capacitance, and we saw the response of those circuits when they are connected in series, parallel, combination. So, today we will see particularly the capacitor and inductor phasor relationship with respect to voltage and current. So, for inductor, let us assume that the current is I is equal to I m cos omega t plus phi, right. So, the voltage across. So, let us see the performance of inductor voltage and current with respect to phasor in the inductor. Let us say the current in the inductor is I is equal to I m cos omega t plus phi. So, as we know that the voltage across the inductor can be defined as L di by dt. So, in this case the voltage would be, if you differentiate the current I with respect to time, you will get minus omega L I m sin omega t plus phi. Now, we discussed couple of lectures back that if you have minus of sin theta, you can represent it in the form of cos as cos theta plus 90 degree. So, the same we have utilized here, and we converted the sin into cos, and now we can write is omega capital L, that is inductance, I m cos omega t plus phi plus 90. So, now how you will represent the voltage in phasor terms? This term is anyway constant. So, you can write it like omega L I m. Then the cos term which you are seeing here, you can represent in the form of Euler form. So, how you will write? You will write e to the power j phi plus 90. So, this would be the phasor representation of the voltage which we just derived. And now, this term you can separate it as e to the power j phi and e to the power j 90. Now, if you see this term, what you will write? As you know that e to the power j phi is nothing but cos phi plus j sin phi. So, instead of phi, if you write 90 degree, so e to the power j 90 will become j, because cos 90 will be 0, j 90 will be simply j. So, this term can be simplified as j omega L I m e to the power j phi. Now, if you see this particular term, this is nothing but the phasor representation of current. So, you can simply write capital I in bold, that shows that this is the phasor representation of current. So, you can simplify the voltage phasor is nothing but j omega L into phasor I. Now, what is this term? This term is basically the inductive reactance. So, in simple term we represent it like X L. So, what does it mean? If you correlate with the Ohm's law, you will see that voltage is represented as R into I. So, if you correlate that Ohm's law with this particular equation, you can easily say that this is something which resists the flow, and that is why it is called inductive reactance in case of inductor. Now, if you plot the current and voltage phasor on the plane, so you will have in the x axis you will have real value, and on the y axis you will have imaginary value, and if you plot current, so it will be phasor will be in one particular direction making phi angle from real axis. So, this would be the phasor of current I. Now, if you see phasor for voltage, if you see this particular equation, you will come to know that voltage is leading current by 90 degree. So, the voltage phasor would be 90 degree leading with respect to current, and it has some value. So, the value would be omega L I m. So, that is what we have derived for voltage. So, here the value would be different, but the current would be lagging with respect to voltage. So, if you see the phasor diagram, it is clear that voltage is having 90 plus phi with respect to real axis, and it is having 90 degree leading with respect to current. Now, let us talk about the capacitor. Suppose the voltage across capacitor is given as V is equal to V m cos omega t plus phi, then how you will calculate the current? You will utilize this equation I is equal to C dV by dt. It means that you have to simply differentiate the voltage term, and you will get current I is nothing but minus omega C V m sin omega t plus phi. Now, as we did in case of inductor, we can replace the sine term with cos, and we add 90 degree to make it positive, because negative sign will be removed here, and it is good for phasor representation. Now, what we can present in terms of phasor? Let us say that a phasor for current I is I in bold, and omega C V m is the constant term, then cos omega t plus phi plus 90 can be represented in Euler form as e to the power j phi plus 90, and then if you separate it, you will get omega C V m e to the power j phi into e to the power j 90, and if you simplify, you will simply get j omega c into V. So, now if you write voltage V is nothing but I upon j omega c, what will happen? The term 1 upon j omega c is again similar to what we saw in case of inductor or what we saw in case of resistance. So, in case of resistance also the term was V is equal to R into I. So, if you correlate, this will also have the property to resist the flow. So, what we will write this will simply write as Xc, which is symbolized as capacitive reactance. So, you can see that both of the terms are similar to what we described in case of Ohm's law. Here, if you plot the voltage and current on the z plane image with the real axis on x axis and imaginary on the y axis, if you plot voltage V, which will have some phase angle phi with respect to real axis, then if you see this particular expression, you will come to know that current I is leading with respect to voltage by 90 degree. So, what we can say that in this case current will lead voltage by 90 degree. So, in both of the cases, whether it is inductor or capacitor, voltage and current would be 90 degree out of phase. So, when you compare with the resistor where voltage and current both are in phase, in this case capacitor and inductor both will be out of phase. In case of inductor, current will be lagging with respect to voltage by 90 degree, while in case of capacitor current would be leading by 90 degree with respect to voltage. Now, let us take one example so that you can better understand the term of phasor. Let us see that voltage, suppose voltage V is equal to 12 cos 60 t plus 45 degree is applied to one inductor having value of 0.1 Henry. If we are asked to find the steady state current through inductor, we will use the term which we just derived, that is I phasor is nothing but V phasor divided by j omega L. Now, voltage phasor you can take from here. So, that is nothing but 12 angle 45 degree divided by j omega L. So, omega is 60, which you can see from here, multiplied by the value of inductor, that is 0.1 Henry. So, what you can write the lower term would be 6 angle 90 degree. Why 90 degree has come? Because j term is there. So, the j can be simply written as 1 angle 90 degree. So, here if you multiply j with 1 angle 90 degree, you will get 6 angle 90 degree as a denominator, and when you simplify, the 12 will become 2 when you divide it by 6, and then 45 minus 90 degree would be the final phase angle, that is minus 45 degree ampere. So, that would be the current value which we get from the inductor, and if you are asked to write in the time domain, you can simply write as, since we know that I is equal to I m cos omega t plus phi is the time domain representation of the current. Here I m is nothing but 2, which we just calculated, then cos omega t is nothing but 60 t over here, and then phi is minus 45 degree ampere. So, with this we can calculate the value of current in phasor domain as well as in time domain. Now, let us talk about the instantaneous power. Instantaneous power is the power at any instant of time consumed by an element or being supplied by any voltage or current source. So, instantaneous power P t absorbed by any element is the product of instantaneous voltage V t and the instantaneous current I t, which is flowing through it. So, in mathematical terms, what we can write? We can write P t is nothing but voltage V multiplied by current I, both are in time domain. So, how we will calculate the value of power? Suppose we have voltage V as V m cos omega t plus theta V is the phase for voltage, and I t is nothing but I m cos omega t plus theta I. So, that is theta I for current. Now, here V m and I m are the amplitudes and theta V and theta I are the phase angles for the voltage and current respectively. Now, if you put these value in the equation, that is P t is nothing but V in time domain and current I in time domain, you will get V m I m cos omega t plus theta V into cos omega t plus theta I. Now, if you do some simple mathematical or trigonometric operation, you will get this term. How you got this term? Now, let us assume that this angle is A and this angle is B. So, if you recollect the previous lectures we discussed, cos A minus B is nothing but cos A cos B plus sin A sin B. Similarly, cos A plus B is nothing but cos A cos B minus sin A sin B. So, if you sum up these two equations, what you will get? 2 times cos A cos B is nothing but cos A minus B plus cos A plus B. So, now if you see correlate this equation with the term of cos A cos B, because A we have assumed that omega t plus theta V and cos and B we have assumed omega t plus theta I. So, now if you correlate and substitute the term of A and B, you will get the equation called 1 by 2 Vm Im cos theta v minus theta I plus 1 by 2 Vm Im cos 2 omega t plus theta v plus theta I, because A minus V will become theta v minus theta I and A plus B will become 2 omega t plus theta v plus theta I. So, in this way we can represent that the instantaneous power is the summation of two terms. Now, if you carefully see these two terms, the first term is constant because there is no time dependent portion available in this particular term. While if you see the second part, it has the sinusoidal part which has a frequency of twice the frequency of voltage or current. So, these two terms are defining the instantaneous power. Now, if you see this term, you can say that instantaneous power changes with time, therefore, it will be difficult to measure. So, what we measure in general? We measure in general the average power because it is more convenient to measure. And in fact, if you see the wattmeter is using is measuring the average power than the instantaneous power. So, let us see how we will calculate the average power from the previous equation which we derived. So, average power we can represent in watts would be the average of instantaneous power over one particular time period. So, how you will represent it mathematically? You will say that the average power P is nothing but the 1 upon T integral between 0 to T Pt dt, means that you are taking the average of instantaneous power over one particular time period. So, what we derived previously? We derived previously the instantaneous power is nothing but one constant term and plus one sinusoidally varying term. So, we will use the same term for Pt here. So, we can write average power is nothing but 1 over T 0 to T integral for 1 by 2 Vm Im cos theta v minus theta I dt, that is for constant term, and then similarly we can write 1 by T 0 to T integral for 1 by 2 Vm Im cos 2 omega t plus theta v plus theta I, and dt term will be there. So, with this you can calculate the average power. Now, you need not to worry about how to integrate these two terms. You can just simply look at these two terms, you can identify what would be the value of average power. How? Let us see the first term. First term is anyway constant. So, the average of the constant will always remain constant. So, this term will remain same as it is after integration, but if you see the second term is sinusoid, and as we know that the average of sinusoid over a time period is 0. How? Let us see, if you see a particular sinusoid, the area under the positive side would be equal for area below the x axis. So, if you take the average over a particular time period t, the positive will cancel out negative. So, eventually the average of this sinusoid over a time period would remain 0. So, we can say that average of sinusoid over particular time period is 0. So, the final term which you will get from the integration which we saw previously, this term will become 0, and finally what we left with is this term, and what we can say that average power is nothing but 1 by 2 Vm Im cos theta v minus theta I. So, this is nothing but the constant term which is left from the instantaneous power expression. So, we can say that the average power P is nothing but the constant term which we have got from the instantaneous power. Now, if you see that particular expression, that is average power P is nothing but 1 by 2 Vm Im cos theta V minus theta I. If you put the value theta V equal to theta I, that means both voltage and current are in phase. So, if both voltage and current are in phase, that means that the circuit is purely resistive. Now, if the circuit is purely resistive, the average power can be given by P is nothing but 1 by 2 Vm Im, because theta V minus theta I will become 0. So, cos of 0 will be 1, and we can simply write average power across the resistive element would be 1 by 2 Vm Im, or simply you can say 1 by 2 Im square R, because V is nothing but I into R. Now, the second case is that so in case of resistive load, you can say that the circuit will always absorb power. In second case, when suppose theta V minus theta I is the difference of angles is 90 degree, that may be positive or negative, it means that the circuit is purely reactive. That means that the circuit is having only inductive or capacitive elements. In that case, what will happen to average power? Average power P would be 1 by 2 Vm Im cos 90, and then cos 90 is 0. So, average power will be 0. So, in this case, what you can say that in case of purely reactive circuit, the circuit will not absorb any average power. So, these are the two important boundary conditions for this particular average power calculation, where you can demonstrate that one is for purely resistive and second is for purely reactive. Now, let us take one example so that you can understand what we discussed till now. Now, if you are asked to find the instantaneous and average power absorbed by a passive linear circuit, and if it is excited by some voltage V, that is given as 120 cos 377 t plus 45 degree. So, the current is also given in this particular element is IT is nothing but 10 cos 377 t minus 10 degree ampere. So, voltage V and current both are given. What we have to do? We have to find out the value of instantaneous as well as average power. So, instantaneous power Pt can be given as multiplication of instantaneous voltage and current. So, here you can simply put the value of V and I. What you will get? You will get 1200 cos 377 t plus 45 degree into cos 377 t minus 10 degree. So, again what we discussed previously, you can say that this is A and this is B. You can utilize cos A cos B value, that is nothing but 1 by 2 cos A plus B plus cos A minus B. When you simplify, what you will get? You will get 600 cos 754 t plus 35 degree plus cos 55 degree. So, if you simplify, you will get one constant term as we got in the case of instantaneous power derivation, and plus one sinusoidally varying term. Here this will be twice the value of original omega. So, you got one constant term plus one sinusoidally varying term for instantaneous power. Now, how you will calculate average power? For calculation of average power, we came to know that the constant term which we get from the instantaneous power is nothing but the total average power. So, from here itself you can say that the average power is 344.2 watt. But how you will verify whether it is correct or not? let us calculate the average power with the equation which we just derived for average power, that is P is nothing but 1 by 2 Vm Im cos theta v minus theta I. Now, put the values of those terms. Here Vm is 120, Im is 10 and cos theta v is 45 and theta I is minus 10. So, if you simplify again, you will get the same value which we just saw in the instantaneous power calculation. So, we can say that the average power which we calculate from the formula or average power we calculate from the instantaneous power constant term of instantaneous power, both are same. So, this you can verify the values. So, with this we finish our today's class. In next class we will discuss about the one of the most important term called RMS values, because whenever you analyze the electrical circuit, you will always get the Vm and Im as represented in terms of RMS value, because in real scenario you will never get peak values as given in the equation or as defined in some experiment. You will always encounter the RMS value. So, we will see how we can derive the RMS value with the help of the peak values and the sinusoidal term. As for example, if you see here, you will always get peak value of voltage and you will always get peak value of current. But suppose if you are asked to find out the RMS value, how you will find, that we will discuss in the next class, and then we will continue with our discussion on mesh and nodal analysis. Thank you.